Last class we were discussing variance and covariance. So, the covariance of two random variables is defined as expectation of x y minus expectation of x times expectation of y whenever it is well defined. Okay. And we said that the random variables x and y are said to be uncorrelated if covariance of x y equal to 0. Okay. And we were in the middle of proving a theorem saying which says that if x and y are independent, then they are necessarily uncorrelated. Okay. But the converse of course is not true. We gave an example, uncorrelated random variables may be dependent, they need not be independent. Okay. So, I will state that the theorem I think I did not state it in very precisely. So, I will state the theorem more precisely today. So, you take this statement rather than the previous one, and I was in the middle of the proof, but let me state the theorem properly. If x and y are independent random variables with expected absolute x less than infinity and expected absolute y less than infinity, then expected x y exists and covariance of x y equal to 0. Okay. So, this is the statement of I stated it in plain English I think yesterday, right. So, this is the proper statement. So, all you need here is expectation of absolute x and expectation of absolute y being finite. Okay. Then in that case you are guaranteed that expected x y exists, and in particular expected x y will be equal to expectation of x times expectation of y. Okay. So, so it is generally not the case that if x and y have well defined, so in this sense finite expected value, it is generally not the case that expected x y is well defined. Okay. But if they are independent, it is automatically well defined, okay. And in fact they are uncorrelated. Okay. So, this is the statement. Proof we started out saying proof we did it for a simple case, right. If x and y are simple, we wrote so we had this kind of a representation, right. I big A I and y is equal to sum over I j equals 1 through m b j I b j, right. Then we wrote out x y as the double sum a I b j indicator a I intersection b j, and then we argued that a I and b j are independent for all I and j, right. That was because x and y are independent random variables, and then we were able to prove that x and y are in fact uncorrelated. Okay. Now, we have to extend it for any non-negative measurable random any non-negative random variables, right. So, this is previous class. So, this was done. So, next suppose x and y are non-negative. Now, what do I do? Consider a approximating sequence, right. So, consider let x n and y n be simple the sequences of simple sequences of simple random variables such that x n increases to x and y n increases to y. Okay. Such an approximation always exists, we know that, right. We can explicitly find such a approximation from below. So, I am obviously heading towards an application of the monotone convergence theorem, right. So, obviously then x n y n increases to x y, agreed. They are all non negative and increasing, right. So, x n y n is also increasing and it approaches x y, correct. Okay. We have expectation of x y, we have expectation of x y is equal to limit n tending to infinity expectation of x n y n y m c t. But x n and y n are okay. So, wait, so x n and y n so the way you can do it is x n and y n in your approximation, right, are independent also, right, because in if you just specifically take the you remember the how we constructed, if you given any measurable function, non negative measurable function g, the way you construct g n, the approximating sequence, you can show that x n and y n are also the approximating sequences are also independent of each other, all right. Since x n and y n are independent by construction, right, this is what I mean, right. So, with the way we constructed the approximating sequence, you can verify that they are in fact x n and y n are in fact independent. Okay. Expectation of x y equal to, so this will be limit n tending to infinity. So, you know that for simple random variables you have shown that independent random variables are uncorrelated, previous lecture, right. So, this will become expectation of x n times expectation of y n, correct. Now, so this limit can be, this is obviously limit expectation of x n's time limit expectation of y n, because both the limits exist, right. Why do both the limit exist? From, well, it is actually because of MCT, right. So, again by, so you apply MCT, so this is limit this times limit that, right. So, the limit of a product is the product of the limits if whenever all limits exist, but here all limits do exist, right. So, that will be equal to, so this is by MCT again, this will be expectation of x times expectation of y. Okay. Any questions? So, you proved it for non-negative random variables. So, I have not assumed here. So, if you notice I have proved this is a very general proof, right. I have not assumed that x is discrete or y is continuous or any such thing, right. I have not assumed joint densities, I have not assumed PMFs, right. It could be a very any general random variable x and y, whenever they are independent they are uncorrelated. Well, I have proved it for the non-negative case, when x and y are both non-negative. If I have to deal with random variables that are possibly negative, then I have to use x plus x minus, right. More generally we write x is equal to x plus minus x minus, y is equal to y plus minus y minus, and complete the proof. This is there in your lecture notes. Okay. So, I am not writing that down. You explicitly compute write x as x plus minus x minus, y plus as y plus minus y minus, expand the whole thing out, and then you can prove that. So, when x and y are independent, x plus and y plus, x plus and y minus, they will all be independent, right. You have to that you can show easily, right, because in fact that is a question in your quiz, right. After all, what is x plus? X plus is max of x comma 0. Suppose you want to show that x plus and y minus are independent, y minus is minus min of y comma 0, right. They are both functions of x and y. So, they must be independent, right. So, all these guys will turn out to be independent, x plus y plus, x plus y minus, x minus y plus, x minus y minus, right, and then invoke this for non-negative random variables and you can get it. Okay. Just write out the whole, write out this product and you will get it. Okay. You have to, that is where you have to invoke this. Okay. If this were not true, then you may have some infinity minus infinity problems. Okay. Okay. Any questions? Okay. So, I am next going to talk about the variance of sum of two random variables, right. So, we know that, so if you have x and y are any random variables, not necessarily independent or uncorrelated or any such thing, we know that expectation is always linear, right. Expected x plus y is always equal to expectation of x plus expectation of y, that is just linearity of integrals, right. But the variance is not necessarily always you cannot always say that the variance of a sum of two random variables is sum of variances, right, that is not true. Okay. So, I will just state a proposition that says if x and y are random variables, then sigma x plus y squared is equal to sigma x squared plus sigma y squared plus twice covariance of x comma y. Okay. So, if you are interested in computing the variance of a sum of two random variables, then you have to sum the two variances and add twice the covariance. Okay. But if x and y are uncorrelated, you can just add the two variances, or if x and y are in particular independent, you can add the variances and say that is the variance of the sum. Okay. Similarly, for n random variables, how do you think this will generalize? If you had sum of n random variables, you will first sum all the variances, plus you will have all the possible covariance, twice all these covariances, like covariance x I h j for all I less than j, right, you have to sum it like that. Okay. So, it generalizes in a straightforward manner. Okay. So, this proving this is very easy, right, you can just write out. So, what is this? This is after all expectation of so this is expectation of x plus y squared minus yeah. So, let me do it like this, minus expectation of, well, expectation of x plus y the whole squared, right. Great. Now, this is equal to this. So, this is equal to that is equal to, you can just expand this guy out, right. So, expectation of x squared plus y squared plus 2 x y minus expectation of x squared minus expectation of y squared well. So, what I mean here is expectation of x plus y the whole square. Okay. So, this is just expectation of x plus expectation of y. Okay. So, then I will get minus 2 expectation of x expectation of y, right. So, then I have what I want, right. So, this and that will combine to give you variance of x, that and that will give you variance of y. So, plus 2 expected x y minus 2 expected x times expected y, right. So, this will be equal to that, right. If x and y were uncorrelated, you will have this term will cancel with that term. So, you will have just the sum of the variances. Okay. So, that is just a minor point. So, generally if you are given independent random variables or uncorrelated random variables, you can add the variances and say that is the variance of the sum, but generally you cannot do that. Okay. You have to have all these covariance terms. Okay. So, if covariance of x y is something positive, the variance will only be greater, right, but if it is a negative correlation, the variance will actually be less than the sum of the variances. Okay. Variance of a sum will be less than the sum of the variances if they are negatively correlated. Okay. So, that is just a minor thing, right. I want to make another definition. The correlation coefficient between x and y between x and y or y and x, it is all the same, is defined as rho x comma y is equal to covariance of x comma y divided by sigma x sigma y. Okay. These are the standard deviations, the square root of the variances, or you can take it as covariance of x y by square root of variance x square root of variance y. Okay. So, this is called correlation coefficient between x and y. So, in some sense this is a scaled version of the covariance. Okay. So, it is like saying, so if x and, so this is somewhat scale invariant. So, if x and y, you are measuring x and y in let us say kilograms as opposed to grams, right, you will get different answers for the covariance, but rho x y will be the same, okay, no matter what units you measure x and y in. Okay, it is like a scale free thing. The most important thing about this rho x y, again rho x y can be positive or negative, right. So, these guys are always, the denominator is always is always positive, of course assuming all this is not 0, right. This is not defined when the standard deviation is 0, but if the standard deviation is 0, then the variables are themselves, the random variables are themselves constant, right. So, except in that case this is well defined and this is positive, and covariance could be positive or negative, right. So, rho x y could also be positive or negative, it can in fact be 0 also, right. So, the important result about this correlation coefficient is it is a number that lies between -1 and 1 always. Okay. So, in that sense it is a scale down, it is a very it is a nice way to represent the covariance, the correlation between x and y, okay, because it is a kind of scale free kind of a thing. Theorem. This is Cauchy-Schwarz inequality. For any two random variables x and y, -1 is less than or equal to rho x y is less than or equal to 1. Further, so this is saying that the correlation coefficient lies between -1 and +1 both inclusive. Furthermore, we can in fact say that whenever the correlation coefficient equals +1 or correlation coefficient equals -1, there is a deterministic relationship between x and y. Okay. Further, if rho x comma y equals 1, then there exists a greater than 0 such that there exists some real number a greater than 0 such that y minus expectation of y equal to a times x minus expectation of x almost surely. And if rho x y equal to -1, then there exists a less than 0 such that all that. So, is the theorem clear? So, this is saying that correlation coefficient is between -1 and 1, but whenever it is equal to 1, then y can always be written as some a x plus b for some constants, right. You can think of just this as a x plus some other constant, and similarly if rho is -1, then y is equal to a x plus b where a is negative. So, there is a deterministic relationship between x and y whenever the correlation coefficient is +1 or -1. So, when that is not the case, they will be strictly between 0 and 1. Okay. This is called Cauchy-Schwarz inequality. So, another way of saying that is absolute covariance of x y is less than or equal to sigma x times sigma y, right. Another way of saying the Cauchy-Schwarz inequality is to say that absolute rho x y is less than or equal to 1. In other words, absolute covariance is less than or equal to sigma x times sigma y, right. Proof. So, this Cauchy-Schwarz, it has a very short proof, but you have to know it. Okay, it is a little bit difficult to I mean you have to know how to proceed with it, because I mean I am just going to copy what I have here. Okay. So, you have to do the, it comes in 2 steps, but you have to know how to do it. Okay. Let x tilde equal to x minus E x and y tilde. So, it is easier to work with the centered versions of these random variables, right. I am just taking away the mean. So, that these guys are 0 in expectation, 0 mean random variables, and all this is a little bit easier, because then you will have y tilde equal to a times x tilde and so on, right. So, with 0 mean random variables all this is very easy. Let blah 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 y tilde equal to y minus E y. Now, I want to show, consider this. Okay. This is what you have to start with. So, with this definition, expected x tilde squared will be variance of x, and similarly expected x tilde y tilde will be covariance of x y. Okay. So, you consider expectation of this big expression, expectation of x tilde minus expectation of x tilde y tilde over expectation of y tilde squared times y tilde this whole squared. Okay. So, I mean, so this is actually just a constant, this whole thing is just a constant, right, and in fact what is this? So, this is like covariance over sigma y squared, is not it? So, I am just considering this. So, I am essentially considering x tilde minus some constant times y tilde, okay, and I am considering the squared expectation of that. Now, this is certainly non negative. Why? Because what is inside is a non negative random variable. So, this is certainly non negative. Now, it turns out that if you expand this out, you get Cauchy-Schwarz inequality. Okay. So, let us expand this out. Well, let us see. So, this is, so this will be like expectation of so does this work out. So, it will give you expectation of x tilde squared so if you do this you will get it. So, okay, so it is a big messy operation. So, you will have this squared times expectation of y tilde squared, right. So, should we just do this quickly, x tilde squared plus expectation of, so this will square, isn't it, this will square. So, I will get expectation of x tilde y tilde squared over expectation of y tilde squared. I will have expectation of y tilde squared the whole squared, but then that will cancel with expectation of y tilde squared coming from here, right. I am taking x square plus y square minus 2x 2 a b if you like, right. So, then I will have a minus 2 a b term, that is minus 2 x tilde well, okay. So, I made a mistake here, right. So, finally, I think if I do that, so far I am okay, I think, right. So, then I will put an expectation here minus 2 expectation of x tilde y tilde, right. So, that much times expectation of x tilde y tilde over expectation of y tilde square. Okay. I think this is correct. Any mistakes? Fine. So, I am taking expectation of x tilde square plus expectation of y tilde squared times this whole squared, right. So, that is what this is. So, there you will have one cancellation here minus 2 expectation of x tilde y tilde times that constant, right. So, I have this guy squared now, right. So, this works out to be, I think this works out to be what I want, right. Is this okay? So, I will have, so for one thing, one of this will cancel this 2, right. I mean this is exactly the same as this, isn't it, except for the 2. So, I can just get rid of that guy and get rid of the 2. So, I think you will agree with that. Okay. So, I think that is all I have, that is all I want, right. So, this is greater than or equal to 0, right, which means I have, bring this to this side, you have expectation of x tilde y tilde squared is less than or equal to expectation of x tilde squared times expectation of y tilde squared, correct. So, this is, so which means the absolute, so if you take square roots, positive square roots on both sides, you get absolute covariance less than or equal to sigma x times sigma y, right, because this is sigma x squared and sigma y squared, right. So, you would have proven the Cauchy-Schwarz inequality. Now, how do you prove this bit? Okay, so this greater than or equal to 0 is for this. Okay, so this is greater than or equal to 0. Okay, so now you have, so if you have absolute rho x y equal to 1, then that means that this is met with equality, correct, which means that is met with equality eventually, correct. So, I have the expectation of a squared, this whole thing squared equal to 0, which means x tilde must be equal to some constant times y tilde, which is what we wanted to prove, correct. In fact, you can identify the constant a as that guy, correct, fine. Okay. Is that clear, the second part of the theme? So, essentially we are saying that this random variable inside this squared must be 0 almost surely. So, which means almost surely y tilde x tilde must be a constant times y tilde, end of story, which is what we have, which is what we wanted to prove, right. Or maybe I will have it the other way, right. I will have x tilde equal to constant times y tilde, which is same as saying y tilde is some other constant times x tilde. Okay. Are there any questions?
So, there is a Cauchy-Schwarz inequality in inner product space and norms. Is it the derivation of that in?
Well, yeah. So, I am getting to that. Okay. So, the question is for so you know that if you have let us say vectors in Euclidean space, there is a standard definition of inner product and right inner product x y between two vectors, and you know that for two vectors in Euclidean space there is this Cauchy-Schwarz inequality which says absolute inner product of x y is less than or equal to square root of norm x times square root of, well, norm x times norm y, right, yeah, norm x times norm y. So, So, this has a very similar flavor to it, right. In particular, what happens is that this covariance of x y plays the role of a inner product, okay, and this in some sense the sigma x and sigma y are playing the role of the norm, okay, right, except these x and y's are not vectors in R and they are random variables, correct. So, this covariance satisfies all the properties of an inner product, namely. So, what are the properties that you want of an inner product? You want symmetry, right, inner product x y should be equal to inner product y x, right. So, that is clearly true, covariance x y and covariance y x are equal, right, by definition they are equal, right. And then what do you want? You want bilinearity, right, bilinearity is if you have inner product a x plus b y inner product with z, you want to become linear, which is also true for covariance, right. And then finally, you want, so and then you want, so then you can prove Cauchy-Schwarz holds, right, Cauchy-Schwarz obviously holds. There is one little thing that remains, you want inner product x with itself is always greater than or equal to 0, correct, and equality holds only if x is equal to 0, that is a property of inner product, that is one of the defining properties of an inner product, correct. So, what is if I claim that covariance of x y is in fact behaving like an inner product, I want to establish that covariance of x comma x is greater than or equal to 0, correct. So, what is covariance of x comma x? Yeah, covariance of x comma x is simply the variance of x, is not it. So, that is greater than or equal to 0, no problem. But if the variance equal to 0, you have to show that x is equal to 0, is that true? X is equal to, so well x is equal to, you cannot say that x is equal to 0, you can say that x is equal to constant, but even x is equal to constant you can only say for almost surely, right. So, there is a little bit of a problem here. So, for one thing you can do is you can just consider 0 mean random variables, right, just consider the, you can think of this x and y's are all 0 mean random variables. If you have non-zero mean, you just subtract it off, right, if it is a finite mean, as long as it is finite you just subtract it off. So, you work with only 0 mean random variables, then this problem kind of goes away, right. If you say that covariance of x comma x is equal to 0, that means x is equal to now 0 almost surely, because these are all 0 mean random variables. But again you have to have this problem, it is not really 0 random variable, it could be non-zero in some set of probability measure 0, right. So, ultimately you have to consider the equivalence class of random variables which are which agree on agree everywhere except perhaps on a 0 measure set, right. If you are willing to consider that equivalence class as the 0 random variable, right, if the set of all random variables are equal to 0 almost surely, as if you identify that as the 0 random variable, the equivalence class of 0 random variables, then you have a, then everything is fine, right, except for this little adjustment, then this is fine, right. Then you will in fact have that covariance of x y plays the role of a inner product in the space of 0 mean random variables, correct. And these guys are like norms, right, and then you have Cauchy-Schwarz inequality holding, and what is so what would you identify rho x y as? So, what is inner product x y, is it the cosine or cosine square, the cosine of the angle between the two vectors, right, right. So, this is like the so rho x y will be like the cosine of the angle between these two random variables. You can think of this as, so x and y are, you can think of them as some vectors although they are random variables. So, this rho x y has the interpretation of cos theta in some loose sense, right. So, this can be made more precise, everything I have said can be made more precise. So, if you consider the class of random variables with 0 mean, and if you are willing to identify this almost surely constant random variables as simply 0, then you can prove that these 0 mean random variables with of course finite, all this well defined, right. For example, variance should be finite and so on, right. Whenever variance is finite, this forms a Hilbert space. Have you heard of a Hilbert space? So, a Hilbert space is basically a complete space with a endowed with a inner product. It is an I told you it is endowed with an inner product, and it is also a complete space because it has, I mean, the values, these x and y take values in a complete space, right. They are, in particular they take values in R in our case, right. So, you can prove that these finite second moment random variables with identifying this equivalence class to 0, right, form a Hilbert space. Okay. It is called L2 random variables. Okay. They have finite second moment, and in this L2 space, which is a Hilbert space, this rho xy plays the role of cos theta, okay. And cos theta equal to 0 means x and y are orthogonal, right. So, uncorrelated random variables are like your orthogonal vectors. Okay. So, this interpretation is quite useful in many areas. I mean, in particular in estimation theory, this plays a, this interpretation is very important. Okay. So, I didn't make this very rigorous, but I just spoke it out, but I hope you are roughly with me on this. Okay. This can be made much more rigorous. Okay. Are there any questions? So, you can remember, so what the take home is that there is this finite mean random finite second moment random variables, these well defined, they lie in the space called L2, which is a Hilbert space, okay. And you can define inner product, cosine, all that is you can do. Okay. Okay, I will stop here.